Good afternoon, everybody. I'm Susanna Bertelli. I'm the head of Education and Public Outreach Service of INFN Frascati National Laboratory. On the behalf of Dr. Catalina Curciano, I welcome you to the 10th webinar of Strong 2020 Public Lecture Series. Strong 2020 stands for the strong interaction at the frontier of knowledge, fundamental research and applications, and that is a project that has received the funding from the European Union's Horizon 2020 Research and Innovation Programme. The Strong 2020 project brings together many of the leading research groups and infrastructures involved today in the study of the strong interaction in Europe, and also exploits the innovation potential in applied research through the development of detector systems with applications beyond fundamental physics, for instance, medical imaging and information technology. The consortium includes 45 participant institutions embracing 14 European member states, one international EU interest organization, CERN, and one EU candidate country. Today's public lecture is devoted to how progress is made in fundamental science, cutting-edge instrumentations. Our speaker will be Dr. Werner Riegler, who is working at CERN. He is an experimental physicist, and he is the technical coordinator of the ALICE experiment at LHC. The abstract involves the basis for progress in our understanding of nature is the precise measurement of physics processes. Using examples from particle physics instrumentation, the role of new tools in major discoveries is illustrated. The state of art of particle detector principles and technologies are discussed, and the challenges for the futures are outlined. For those who want to know more about the Strong 2020 project, you can visit the website here reported. So I remind you that you can write your question in the chat, and at the end, we will answer to a few of them. Dr. Riegler, the floor is yours.
Thank you. So let me try to share my screen. Okay, share. Now make this to full screen. Okay, so just to verify, you can still hear me?
Yes.
Okay, good. So thanks a lot for the invitation to give this lecture. I will talk about how progress is made in fundamental science. I will give a lot of examples from particle physics. This is where I'm working. The picture that you saw just before from me, this has been taken 30 years ago. And as you can see now live, I have not changed at all in these 30 years. So just to prove that particle physics is a very healthy environment. So let me start with a quote from Freeman Dyson, whom you see here, eminent physicist, who wrote in his book Imagined World about scientific revolutions. And he quotes that there are different types of revolutions in science. He quotes one that he calls concept-driven revolution, which he says are where we explain old things in new ways. So this means theoretical discoveries like quantum mechanics, relativity, and so on. And then he talks about tool-driven resolutions, where we discover unexpected things that still have to be explained by having new tools. And he shows that this is happening much more often. So just an example here. These are classic heroes of physics. Einstein, who is famous for theory of special and general relativity. Schrödinger, famous for discovery of quantum mechanics. Feynman, quantum electrodynamics. And here we have Englert and Higgs, who predicted this Higgs particle. So these are people who discovered new theories, if you want, new concepts to explain data or unexplained physics effects. Now here are some more heroes from this context, but now these are people who invented tools. They are not as famous as the others, but still in our field, of course, well known. There's Wilson, who invented the cloud chamber, Glaser, who invented the bubble chamber, Charpak, who developed the multiproportional chamber, and Simon van der Meer, who did the stochastic cooling, allowing the collision of proton-antiprotons for the discovery in the W and the C. So these are people who are known and who made important contributions by inventing a tool that made major discoveries possible. Here you see a few more heroes from this context. There's Lise Meitner, a radiochemist who discovered nuclear fission. This is Marietta Blau, who was the first to develop photographic emulsions that were sensitive to elementary particles. This is C.S. Wu, who did the first experiment showing parity violation. And here you see Marie Curie and her daughter Irene, who made, of course, important contributions to nuclear and particle physics. If I would make a quiz now on what is the difference between the previous slides and this one, of course, the first thing you would say is these are women and there were men on the slides before. But here, what is evident is that these people, Meitner, Blau, and Wu, they did not share a Nobel Prize, while the others did, which is, of course, a shame. I mean, Lise Meitner had to leave Germany in 1938, and Hahn and Strassmann then got the Nobel Prize for discovery of fission. Marietta Blau, she had to leave Austria in 1938, and also later Perkins got the Nobel Prize for discovering the pion with her techniques. And Wu also, she made this experiment, but then Young and Mills got this Nobel Prize for the theoretical explanation. So these are certainly all heroes of experiments and particle physics that where it's a shame that they didn't get the Nobel Prize, but certainly, I mean, we should list them among all the others that I just showed. So now, staying with Nobel Prize, this is something I always show to students. So if somebody is really bound to win the Nobel Prize, I always want to show that doing experiments in instrumentation, there is a better chance. I made some statistics on Nobel Prizes. Of course, these are completely biased and personal statistics because I want to make a point here, but all these, you can, of course, do your own statistics. So when looking into standard model related physics, I counted that about 56 persons who got the Nobel Prize for experiments in instrumentation and 31 for theory. And you have people like Wilson, Glaser, Charpak, who really got only for the development of a tool the prize. I mean, definitely Marietta Blau should be here in this list for the discovery of, for the development of this photographic technique. So anyway, here I just want to show if you're bound to win a Nobel Prize, then go to experiments and tools. You have a twice larger chance than if you become a theoretical physicist. So now, what are we talking about? What is our, what are we studying? It's the present knowledge of physics is summarized in the standard model of particle physics and in the general theory of relativity. So the standard model contains all the known elementary particles and their forces. So we have the matter particles, that's what matter is made of. And then we have the forces between the particles, which in this formalism of quantum field theory are also mediated by particles. So also forces are represented by particles. So this is the strong electromagnetic and weak force. And then there is this famous Higgs particle a bit outside that is there to give consistently mass to all these particles without destroying the important symmetries of the theory. And this has been found in 2012 after a very long search of many decades, and somehow this completed this theory of elementary particles. On the other side, we have general relativity that holds firm since almost 100 years now, or more than 100 years. And all these theories are verified and confirmed quantitatively with incredible precision. So at this moment, from these theories, there's no hint where to find solutions for unresolved questions, like, for instance, dark matter. It's flying around in front of our nose. We have no clue what it is. There's matter-antimatter asymmetry, which in the universe, which is not explained with present theories. There are questions like dark energy, principal formal questions about how quantum mechanics and gravity can be consistent in the very early universe. So these are all unanswered questions, and we need new tools and tricks to measure, to make progress. The problem is it's very difficult to find out what's wrong about a theory if it's confirmed with all the experiments. Okay, there's a very strange situation in history of science, that we have theories that work perfectly with all experiments, but we know they are not the right ones, and we have no hint. Just imagine you are in 1932, okay? You just know that the proton, the neutron, and the electron exists, and now from this you have to guess quantum chromodynamics, okay? There's simply no way whatsoever to do that, okay? That needed in the 1950s, all these elementary particles that were discovered, some symmetries weren't seen, then there were all these resonances measured, and then Gell-Mann postulated the quarks, and then the dynamics of the quarks made quantum chromodynamics. But that needed all these experimental data of many decades to discover. The same is true for quantum mechanics. I mean, there was, since the 1850s, these spectral lines observed. There was the black body radiation spectrum, which was completely unexplained with the known theories at that time. And then people like Schrödinger, Heisenberg, they came along and found a mathematical scheme or the theory to explain it, but they had a wealth of experimental data to look at. And this is what we are missing at the moment to find a more fundamental theory. So we simply have to develop tools to measure more precisely such that we can get a hint where an underlying theory would be. So let me just give you an example of the development of such a tool at the early 20th century, which was an accidental development of a particle detector. It's about the cloud chamber. The whole thing started with meteorology. There was a Scottish meteorologist who wanted to know how clouds are forming. It was evident that cloud droplets form around condensation nuclei. It's not enough you have saturated water vapor, you need some dust such that clouds can form. So he built a so-called dust chamber where he did controlled experiments. He mixed dust and he then expanded the volume to produce saturated water vapor to observe the condensation of water around dust particles. So this was just to see how clouds are forming. Now, there was a suspicion that clouds have something to do with electricity, and this is where Wilson came into the game. So he also was a meteorologist, and he came to the Cavendish laboratory, where also there was J.J. Thomson and later Rutherford, but he wanted to work mainly on meteorology questions. So he built a chamber where he could produce saturated water vapor, but without any dust. And he just wanted to put ionization inside to see whether that's also responsible for cloud formation. What he used for this experiment were X-rays. They were discovered by Röntgen just around that time. And Wilson used this X-ray tube to radiate his chamber because it was known that X-rays produce ionization. And he indeed found a very great increase in the number of drops. So he confirmed the hypothesis that also ions or electrical charge can be the source of cloud formation. The same he could observe when using uranium rays or radioactivity that was discovered just a bit earlier. Now, what he then wanted to find out is how raindrops are formed out of these small droplets. So he used something called high-speed photography, which a guy called Worthington has developed in around 1908, where with sparks of light, he could really make a sequence of pictures really showing very fast dynamical processes. So he used this to see how his little droplets would form raindrops. But to his surprise, when then he looked at the photographs, he saw these particle tracks. So here he used an alpha source to produce the ionization in this chamber. And what happens is that the alpha particle moves through the the air in the cloud chamber. It ionizes the air, and these ions, they are condensation sources for the water vapor. So you get lots of little water droplets along the track. And then even without photography, with a bright lamp, he started to see tracks in his cloud chamber. So by trying to do meteorology experiments, he accidentally developed one of the most important detectors in the first half of the last century. So here you see his cloud chamber. This is the volume where you produce the supersaturated water vapor. This is to produce this under pressure. And in 1911, he made pictures with this. These are pictures from Wilson of X-rays. So each of these tracks is one scattered electron, a Compton electron from an X-ray. So these are many Compton electrons produced by X-rays. These are later pictures where an alpha source is put in a cloud chamber, and you see all these individual alpha particles. They all stop at the same distance. And the reason is that all the alpha particles have the same energy at the start. So when they lose energy, they all stop at the same point. So it proves that these alpha particles, they are monochromatic. Here you see one alpha particle shooting a bit further out, and this is a very rare nuclear transition where you get a higher alpha particle energy. Just to illustrate that, I mean, with this cloud chamber, you could really see single particles. You have to imagine about 20 years before that, the discussion whether atoms exist or not was still debated. And now with this detector already, you could see individual ones and measure them very precisely. These are then famous discoveries using this cloud chamber. This is Anderson, who found the positron. So this is a particle that is moving, making a track in the cloud chamber. It moves through a metal plate, loses some energy. Everything looks exactly like an electron. But if you're very sure about the orientation of the magnetic field that is bending this particle, then you can claim it's a positron. So this was the first antimatter particle discovered. In the 1930s, there were already triggered cloud chamber experiments. This was Blackett and Occhialini, who had a cloud chamber that was triggered by a stack of Geiger tubes. So if there would be an electromagnetic shower here, the Geiger tubes would fire the expansion of the volume, make the saturated water vapor, and the ions still being there would produce then this track, and a camera was automatically then started. And here you see the timing of the event was done by just taking on the picture or a clock that was sitting there. So this is already an example of a triggered experiment, something we do, of course, all the time nowadays. And with these kind of arrangements, Anderson and Neddermeyer, they found the muon in 1936. Also, the muon was a very, if you want, accidental discovery. Isidor Rabi said, who ordered this particle? Okay, nobody had asked for it. It was not necessary in a theory. So as you see, this detector that was accidentally discovered by a meteorologist played a fundamental role in particle physics. In the 1947, even strange particles were for the first time already discovered with these cloud chambers. Here you see them, they were called V particles because they have this characteristic decay pattern. So these strange particles, which now we call them lambdas, lambda 0 and K0, you don't see a track because they are neutral, but they decay into two charged particles, and then you see these tracks from the charge. So strange particles were already discovered with these cloud chambers. So then on this analogy to the cloud chambers, the bubble chamber was developed in the early 1950s. So instead of condensing water vapor on the ions, the principle was used the other way around. You have superheated liquid, and if you have a charged particle moving through depositing energy, then you get little evaporation or little boiling bubbles around the track, and you can get very precise measurements. And this is one of the iconic discoveries made with such a bubble chamber, the first measurement of this omega minus particle at BNL in 1964. So you see very complicated decay patterns, even with some uncharged invisible particles, but from the full reconstruction, you can be sure that this is this kind of decay. Now, what I showed up to now were techniques where you would make imaging of your particle tracks. I mean, cloud chambers, particle chambers, they were really taking photographs of these particle events. Here's one example, which is a more electronics type coincidence experiment. Here you don't make an image of a particle, but you find some clever tricks to prove the existence of a particle. This was Chamberlain and colleagues who wanted to prove that the n-type proton exists. So they took the beam from the bevatron on some target, and among the secondary particles here, they suspected that an n-type proton should be produced. So first of all, they used a bending magnet to select a certain momentum of a particle and a certain charge. So they looked for a negative particle. So they bent out negative particles of a given momentum here. Now, to find the mass of this particle, okay, you still have to measure the velocity, okay? So you know the momentum from the bending, and now you measure the velocity by two techniques. One is a Cherenkov counter, and the other just time of flight, okay? Just the time the particle flies between two scintillators. By looking at the signals, they found that this was consistent with the mass of the proton, but it had the opposite charge, so it proved the existence of the n-type proton. So this is more a logic coincidence experiment, very different from cloud chamber photographs. And here is another example of such an experiment that is more on this logic coincident type. This is the first measurement of the neutrino. This was in 1959 by Raines and Cohen, who used a detector close to a reactor where they suspected that neutrinos are produced, and they wanted to see the inverse beta decay. So usually a neutron decays into proton, electron, antineutrino, and the reverse reaction is that an antineutrino hitting a proton should produce a neutron and a positron. Now, if you use this arrangement where you have water where you put some cadmium, if this neutron and E plus positron are produced, the positron will annihilate immediately with an electron. So you get two photons. So you measure these photons or the charge they deposit. And then the neutron, it needs some time to moderate, okay, to get to the energy of the thermal energy of the water. And then the cadmium has a very large neutron capture cross-section. So the neutron is captured by the cadmium. This excites the cadmium, and then you get a cascade of photons. Now, this moderation takes about 15 microseconds. So the signal would be that you have a signal from the plus minus annihilation, and then 15 microseconds later, a photon cascade. And this fingerprint of signal, if you want, was observed, and this proved the existence of the antineutrino. Okay, so this is very different from a photograph of particle tracks. It's more an electronics logic experiment. Now, what we have nowadays is somehow a combination of these imaging detectors and of electronics detectors. If you want, we take an electronics picture of all particle collisions, and these are typical event displays from an experiment like the LHC. Now, these detectors now, okay, have grown to quite some size, and it's quite a long path nowadays to get from detector concepts to physics results in these very large installations. Let me just show you the principle of what's happening at CERN at this moment. So the big machine that is colliding particles is the Large Hadron Collider. At the time of Wilson, this was still either radioactive sources or cosmic rays. But as of the 1950s, the energy frontier was taken over by the accelerators, and now we have the LHC as the most powerful one. This is the footprint of the accelerator. You don't see anything on the surface. This is 100 meters underground, this 4-meter tunnel. And then we have these collision points where the big detectors are installed. These are the 4 large LHC experiments, the Atlas, CMS, ALICE, and LHCb detector. For the size, I just draw your attention to these 2 discs you see here. So on this photograph, you see the people here, and these are these enormous discs. So these are quite large assemblies that took really almost 2 decades from development to really full functional installation. This is a picture from the ALICE experiment that I'm very proud of. You see me here in 2009 closing a 350-ton door just with my force. I have a bit of help from a hydraulic check, but this is okay, not important to mention. Anyway, this was the end of Ali's installation in 2009, also very big magnet. Here you see the CMS detector with the installation of some forward detector, and here the LHCb experiment. So these LHC experiments are really very large installations. And here you see a few of the first event displays from these detectors. So as I said, this is looks similar to a cloud chamber or bubble chamber photograph, but now it's fully electronic, and it has, of course, the advantage that you can take many more data, much higher collision rates. Just to show you here about collision rate. So with bubble chambers or cloud chambers, okay, you can take maybe 10 events per second, not more, because in the bubble chamber, you have to clear the bubbles, you have to compress and superheat. So 10 hertz was already quite impressive. Now at the LHC, we don't look at 10 collisions per second, we look at 1 billion collisions per second. So the event rate is about 1 gigahertz. And you remember it took about 2 years to find the Higgs particle with this 1 billion collisions per second. If you want to find the Higgs particle with a bubble chamber, it would mean that you're sitting around for about 200 million years, okay? So we should have started when the first dinosaurs started to walk on Earth. So clearly this was not fast enough. And for the high Lumi LHC, this will be even increased, so we will have 4 billion collisions per second. Of course, this is too much to be written to permanent storage, so there's some selection with some fast hardware trigger. So the first level trigger, as we call it, selects, divides the rate by a factor 40, and then in a more fine selection in a computing farm, the rate is again decreased such that we have about 5 to 10,000 per second that go really to tape. But I mean, we inspect and select really 4 billion collisions per second. The reason that we need so many collisions is that the heavier the particles are that we want to produce, the smaller the cross section is to produce them. So that we need an enormous number of collisions to produce a few of them. So now, how to make discoveries? Also, there things are not as easy nowadays as they were in the 1960s. Here, again, this discovery of the omega minus particle. Here, the one picture was enough to claim a discovery. So we call this background free, which means there could be not possibly any other event that could fake such a signature. So these people were confident enough to take this one picture and claim the existence of this omega minus particle that consists of these 3 strange quarks. Now, nowadays things are a bit more difficult. Here you see candidate Higgs events. For instance, here Higgs going to 4 electrons, here going to 4 muons, Higgs decaying to 2 muons, 2 electrons, or to 2 photons. But they're called candidate events here because there are many other processes that can also produce these kind of signatures, okay? You can have direct quark-antiquark annihilation to produce 2 photons. So a single event doesn't tell you anything. You have to produce many, many of them, and then you make the invariant masses of these particles. And then the background, so-called background, will be on some kind of smooth distribution. And if you see a bump somewhere there, then this is the particle. There's just a higher probability to produce these 4 muons at a given mass, or these particles at a given mass, and this is how then you can find your new particle. So in most of the physics processes, a new particle cannot be seen in a single event. It can just be seen as an excess of events above an irreducible, which means indistinguishable, background. Okay, so this is the typical way, and this is also why we have to run the LHC and experiments for such a long time with many collisions, because in order to see these signals above background, we need an enormous amount of collisions. So now just a few things how these different detector types developed in the past and how they scaled, to see a bit what we should maybe do in the future. So if we look at astronomy and particle physics, if you want, the iconic starting points for astronomy are these telescopes. I mean, the refractor telescope from Galilei and the reflective telescope from Newton from the 17th century. And for particle physics, the iconic starting points, if you want, are the Wilson's cloud chamber to take the pictures, and then the Rutherford Geiger counter from 1908, which is one of the first electronic particle detectors. Okay. Now, these things, of course, have developed and grown in size. This is the VLT telescopes in Chile from the European Southern Observatory. So the principle, if you want, is the same. Here, there are huge mirrors collecting light, but of course, the use of these principles has advanced significantly. The same is true here. We have the cloud chamber that was imaging cosmic rays. Now we have the LHC producing high energy particles and detectors that are producing the images of the particles. The principle again is the same. We have ionization that produces tracks, but of course the use has completely changed here. Here, just to illustrate a bit how in the astronomy and astrophysics the performance of the detectors was boosted. So if you have a telescope, I mean, that's the equivalent somehow of the LHC machine, but the detectors, okay, for astronomy, first people were looking with the eye. Then, of course, the sensitivity was boosted a lot by using photographic plates. Okay, you could expose for a much longer time, see much fainter objects. And now with electronics detectors like CCDs, you get these fabulous pictures. I mean, this is from the latest space telescope, a CCD image with fantastic detail. So even if the telescope type, I mean, it's the same thing. You just have a mirror. The readout is completely different and is boosting a lot the performance. And the same we have, of course, in our particle detectors. The cloud chamber, there were photographs taken, the bubble chamber, even much more precise photographs. And now we take these pictures with our big electronic detectors. So the principle is the same, but this is, of course, much boosted by technology that was developed over the last century. So now, if you look to the future here, if you look for telescopes, I mean, this is the Paloma telescope that was used a lot also by Hubble and colleagues. Now, there's the VLT and then the ELT that is being built at the moment in Chile. These are not just scaled up versions of an old thing. I mean, they're of course bigger, but here with the VLT, for instance, there's the interferometry between the different telescopes that boosts a lot the angular resolution. And with the ELT, there will be these mirrors that will be adjusted very quickly in order to correct for the atmospheric scintillations and hopefully get pictures that are close to the ones you could get in space. So people are sometimes saying we're just scaling up things without making new things, but that's not correct. They get bigger, but there's a lot more technology and new ideas inside. The same is for accelerators. I mean, the accelerators got bigger and bigger over time. The PS from 1959, the SPS 1976, and now we have the LHC. And there are plans for the future circular collider. But again, they are bigger, but not just scaled up versions of the old thing. The FCC, for instance, when there's an electron-positron machine inside, the luminosity will be 100,000 times larger than what was at LEP. Okay, so the entire program at LEP, which took 10 years, will be done in less than an hour at the FCC. Okay, so it's not just blind scaling up. There's a lot of new technology also in there that boosts the performance with respect to the previous machines. So let me go a bit more now into details and principles, because the principles, they usually stay the same. Here I just want to show a bit how we detect our particles and what is at the root of all our particle detection in high energy physics. So the basis of most of our particle detection is really the electromagnetic interaction of particles with matter. So if this here represents the material, okay, the detector material that the particles are moving through, so through the charge, electromagnetic interaction, these particles that fly through our detectors, they are exciting and ionizing the atoms. And then the de-excitation produces light, which can be detected, or the ionization can be detected by other means. Okay. In the cloud chamber, the ionization was the source of the condensation. In the bubble chamber, it's the source of the bubbles that you photograph. And in our detectors, we have tricks how to measure the charge. So this is at the basis of all our tracking detectors. And then there are other effects. One is if a particle gets close to the nucleus, it's deflected, and this produces scattering. It's an effect that we want to avoid, so we want to make detectors very thin to limit that. And in this deflection, there's something, the charge is accelerated, and it can emit Bremsstrahlung, and this is all at the basis of the electromagnetic calorimetry, where electrons are accelerated close to the nucleus, they produce high-energy photons, and there's a cascade of electrons and positrons, which is used for energy measurements. Okay, so all these are really at the heart of all our particle detection. And then there are two more electromagnetic effects that are more related to the material as a whole. There's Cherenkov radiation, where if the particle is faster than the speed of light in the material, you emit Cherenkov radiation, so you can measure velocity, and transition radiation, a related effect where you produce X-rays, and it's also an effect that allows to measure velocity or the gamma factor of a particle. So these are the electromagnetic interactions that are at the basis of all our particle detection. Now, there's also a trick we use to measure particles that do not interact. It sounds first strange that it's possible that we can measure particles that don't interact with our detectors, but there we can use the trick of momentum conservation. So if you collide two particles of the same mass, then the total momentum of the system is zero. And because momentum is a conserved quantity, also after the collision, it has to be zero. And if you find a missing momentum afterwards, and if you're sure that your detector doesn't have any cracks where they disappear, then you know that it was a particle that didn't interact. And this is how we measure neutrinos. So we measure neutrinos by not seeing them. This is what's said here. He says, did you see it? He says, no, nothing. And he says, well, then it was a neutrino. That's really how we do it. This is an example here, a W particle produced in Atlas. So you have a high energy electron here. And then if you sum up all the momenta from these particles, all these transverse momenta, you find that there's a big transverse momentum vector missing. And this is actually the neutrino from the W decay. Okay, so we even can measure particles that do not interact by the trick of momentum conservation. Now, here you see many, many particles that I wrote on a slide before the advent of PowerPoint. And these are about 180 selected particles. In the particle data book, you find, I don't know, between 400 and 500 by now. And people always ask, how can it be that if we have our events in our detectors, how can we distinguish which is which from all these different particles? The point is that most of them, or almost all of them, are very short-lived. If you look which particles live long enough to leave a track in our detector, you just find this list, okay? All the other 400-500, they decay on the spot. You will never see a track. You just reconstruct them through kinematic relations. And with these particles that can leave a track, you see that there are some that are very short-lived and they decay after a very short time. So they decay inside our detector. And this is an important signature to identify them. These are the B and the D mesons that we can see with these so-called secondary vertices. Okay, so from the hundreds of particles that are listed in the PDG book, there are only 27 which can be really seen flying through our detector. Okay, 13 you can see them, but they decay inside our detector. And then we have 14 remaining particles that could really be inside our detector. And from these 14, we have the electron, muon, photon, pion, kaon, neutral kaon, proton, neutron. These particles are by far the most frequent ones. So in the end, our detectors, they have to measure these particles and identify them, and everything else is then reconstructed mainly by our PhD students from all these data. Okay, so now this means our detectors are really built for the interactions of these particles. So if you see event displays like this, okay, all these particles you see are just from this list of these 8 particles. So fortunately, they have very different behavior, and this is how we can identify and distinguish them. Okay, so the electron is very light, 200 times lighter than the muon, which makes the big difference for Bremsstrahlung. And the photon has no charge. So these are the 3 we can easily distinguish, and they take part only in electromagnetic interaction. All other particles, they have strong and strong interaction. So pion, kaon, proton, they're charged ones. They have different mass, so this is the trick to distinguish them. And the neutral hadrons, the kaon and the neutron, they have no charge, so they don't make tracks, but then they make showers because of the strong interaction. So the difference in mass, charge, and interaction of these particles gives the chance to identify them. But I mean, our detector setups with the sizes, the different types are really, they look like this because of these fundamental properties of these particles. If these numbers would be different, our detectors would look completely different. Okay, so here this is illustrated a bit more in detail. So if you have an electron, you see a track because it's charged, and then it makes an electromagnetic cascade because it's very light. The muon is similar to an electron, okay, so it makes a track, but it's heavier. It doesn't make Bremsstrahlung, so it just moves through a lot of material without being stopped. We can see it in the muon system. And then the hadrons, we also see tracks because they are charged, but then because they're heavy, they don't make electromagnetic cascades, but then they make a hadron cascade in the hadron calorimeter. And the neutral particles, they don't make tracks because they don't produce ionization, but then again, they get absorbed in cascades. This is how we see a photon or a neutral kaon. So these are the tricks. I mean, the properties of these particles really define how we measure them. So let me just go into a little very special detail of these detectors now, about the principles, how we are really now measuring the ionization that these particles produce in order to get the point. As I said, in the cloud chamber, bubble chamber, the ionization is really producing the droplets, which could be photographed. What we do in our detectors is we look at induced charges. So we use this principle here, where you have a charge in front of some kind of metal plate. And if you have a charge in presence of a grounded plate, this charge will induce a surface charge distribution on this plate. Okay, this is what we all learn in our first year of university physics. Now, if you move this charge up and down, okay, this distribution here changes. Okay, if you go closer to the plate with the charge, this charge distribution is more peaked, but there will be no current flowing between ground and this plate. Okay, the total amount of induced charge is always just the negative of this one. But now if you segment your grounded plate into strips, then suddenly if you move the charge close or away, then you redistribute the charge on the surface. It means there are currents flowing between these metal electrodes and ground. Okay, and if now we put our amplifiers here, then we can measure these currents and we can find out about the presence and the position of a charge. Okay, so this is how we use the charges that these particles deposit in our detector to measure the position of these particles. Okay, that's the principle. Now, there's one interesting theorem that we use a lot to calculate these signals. It's called the Rameau-Shockley theorem, where if you have these metal electrodes, okay, which are our detector electrons, could be the wires in a wire chamber or the readout strips in a pixel detector. These are these electrodes. And if you have charges moving from one point to the other, okay, then this induces currents that are flowing through our electronics. Now, one can calculate it by electrostatic solutions of the Poisson equation with these charges, but there's a trick you can use. Use the same geometry, but you remove the charges, and then you produce the so-called weighting fields just by putting one of the electrodes to unit voltage, and you record the electric field. And if you have this, okay, through this formula here, you can then calculate the signal for any charge movement between these electrodes, okay? So this is the trick we use to efficiently calculate the signals that are induced by the movement of the charges in our detectors. So this is this Ramo-Shockley theorem from the 1930s. Now, I played a bit with a student, and we did an extension of the theorem, which, if people are interested, you can see here. This is an extension to the full Maxwell equations of this kind of theorem, and it's based on Lorentz reciprocity. So just to show you what it is about, it's similar to what we said before. So if you have now a detector, okay, and this entire detector is encoded in a position and frequency dependent material, okay, so out of these material constants you can build up your full detector. And then somewhere in this assembly you have a charge that is moving. This is producing an electric field, electromagnetic radiation, whatever you want. And then you measure your signal, which is some voltage, some field integral along a certain point, okay? Now, to calculate this, again, through this Lorentz reciprocity theorem, you can remove the charge here. You put along your measurement path in your detector a delta current, which produces a time-dependent weighting field. And then you just convolute this weighting field with the charge movement, and you get your signal, okay? So this is this extension of the Ramo-Shockley theorem to the full extent of Maxwell's equations, just to show you how powerful this can be. If you assume now you have an electron that is, let's say, moving in the galactic magnetic field, producing synchrotron radiation, and then you have your big radio telescope, usually you would calculate this by producing the electromagnetic radiation, propagating this electromagnetic radiation, then you fold it with the antenna response, and then you get your signal. So with this theorem, you can do the other way around. You put a delta current on your antenna, you get a time-dependent electric field that you can calculate, and then you just convolute this field with the movement of the charge, and then you get what the antenna measures, okay? So if you want to measure synchrotron radiation, you can as well calculate it with this trick. So it means we have now turned also radio astronomy into particle detectors, if you want, with this theorem. Anyway, this was a very specialized thing, but okay, I played a lot with these things in the past, and I think it's a very cute trick that you can use to calculate how electric charges that are produced in our detectors are converted to signals. Okay, so in the last 5 minutes, I want to just come back to some detector technologies that are being developed at this moment that are somehow making the forefront of particle detection. This example here is from the experiment I'm working on, from the ALICE detector. It's about pixel detectors. In conventional pixel detectors that are used at present, they are built in the following way. So you have a sensor with all the pixels, and then the readout electronics is on a separate substrate, on a separate wafer, and then you have to solder them together with these bump bonding techniques. Okay, so you really have, for each pixel, you have a readout electronics, and this is on a separate wafer, and you have to solder them together. They are so-called hybrid pixel detectors, and in Atlas, for instance, there are 100 million of these pixels. So, of course, since a long time, there were ideas and developments to try to avoid this soldering and to make one silicon substrate where you have the sensor and the electronics on the same substrate. And this was realized on a large scale in this ALICE pixel detector that we just installed. It has about 10 gigapixels, 10 billion pixels, and they are indeed the electronics and the pixel, they are on the same substrate. They're so-called monolithic pixel detectors. We replaced the entire silicon detector in ALICE by this monolithic silicon detector, and we also have a forward silicon tracker using this technique. So this was a major step forward because you can get very high measurement precision. And the important thing is very low material budget. I showed before that you have this effect of multiple scattering, where particles moving through material, they are deflected. And that, of course, screws up the measurement. So we want very thin sensors. And by having these very thin monolithic sensors, we can get to very low numbers in material for our detectors. So as I said, it's 12 gigapixel. It's quite a large assembly for such a pixel detector, 1.5 meter long, about a meter in diameter. And these are these very low mass structures here to make sure we have not too much material. Now, there's a very exciting development ongoing at the moment. The point is that on this silicon, the whole electronics, also in all our microchips and so on, the electronics is only in the first 10, 20 microns of the silicon. Okay, the rest of a silicon wafer, which is around 300 micron thick, is just support structure. It's not used. So what is possible is you can make these silicon wafers very thin. Okay, because it doesn't. The electronics will still be there, and also the sensitive layer of 25 microns. So if you thin them down to something like 20, 30 microns, they are still functional. But now you can bend the silicon, okay? And so we did already tests to see whether the chip still works if you bend it, and this was successful. Now, there's one other trick used to make a large chip, which is these electronics chips. They can now be made wafer scale because there is this so-called stitching technique where you can connect the individual reticles on a wafer to one large-scale wafer. So that means we can really make a detector that finally has no support structure. Okay, it's a super thin detector that you just bend around the beam pipe, and you get ultra low material budget. You see here it's less than 0.1% of radiation length, and now already the beam pipe that is around the vacuum of the LHC is already representing more material. So at some point we have to see how we even go inside the beam pipe with these detectors. So this means we have an ultra thin detector. It's just one big chip. We can even bend it around the beam pipe. It's something people dreamed about since a long time. And this is being developed now, and hopefully we can install this in the long shutdown 3 in the center of the ALICE detector. Okay, so yeah, just to conclude a bit on what I tried to tell you now with this a bit random walk to questions of instrumentation. So as I tried to show, there was impressive progress in fundamental physics over the last decades due to all these tools that were developed. It's clear at this moment we need new experimental data and new tools to go beyond current knowledge. We need hints where a more fundamental theory could be. We really have to improve by orders of magnitude, because a fundamental theory underlying the standard model of particle physics and general relativity might be very difficult to reach. It could really be very, we have to measure maybe for a long time until we see deviations. We should just keep in mind that in particle physics, we are very impatient. I mean, we always think we get a new particle every day, like it was in the last decades. If you look at Newton's theory of gravity, which he developed in the 1660s, it was in perfect agreement with all data up to the beginning of the 20th century, okay? Despite all, I mean, celestial mechanics calculations, observations, and so on, and only around 1900, there was this deviation of the perihelion motion of Mercury by 43 arc seconds per century. So extremely small deviation from Newton's theory. And this was the first experimental evidence for a more fundamental theory, which was Einstein's general theory of relativity. So these were 250 years of precision calculation and precision measurement until a deviation was found. Particle physicists are already screaming if for 10 years they don't find a deviation. So I think we really have to be a bit more patient. Now, I also tried to show that new generations of scientific instruments, telescopes, accelerators, detectors, they are not just scaled up versions of previous ones. They have vastly improved performance in every corner. And it's clear to me that, yeah, we really have to look into new tools. The next scientific resolution definitely needs new tools, more precise measurements. Okay, I'll leave it at that. Thanks for your attention.
Okay, thank you, Dr. Riegler, for this very nice overview. So a few questions. How can you detect neutrons?
So I did not show this in detail. So neutrons have no charge, so they do not ionize material, and this is why we don't see them in the tracking detectors. But what neutrons do is they have strong interaction. So if we put a very large amount of material in their way, there's an effect, a strong interaction shower. They produce a cascade of particles. And in this cascade, again, you get charged particles that can produce ionization, and then we can measure them. So if you want, through the strong interaction effect, we convert neutrons again into a cascade of charged particles. And these charged particles we can then measure with our standard ionization techniques.
Okay. How long does it take to build a detector like the one you show for the Alice experiment?
So yeah, all the LHC experiments, all these detectors, so the concepts for the detectors were developed in the early 1990s. Okay, then we had the technical design reports by, let's say, year 2000 at latest. Then the construction took place between 2000, 2005, 2006, and installation up to 2010. So I would say it was 20 years from the first concepts to really having the object ready for operation. Okay, and then the data taking started, and this is now planned. I mean, we did a decade of data taking already now, and there are 2 more decades planned for this data taking. So these are certainly long-term experiments.
Okay. I think that we can stop sharing your screen right now. And which criteria you apply when you choose which kind of detector to use in an experiment?
So yeah, now the so it depends, of course, what you want to measure. The Atlas and CMS detector in this specific example, they are called general purpose detectors. So they were designed to just try to cover the full potential of the LHC. In ALICE, for instance, it's specialized to heavy ion collisions. So there we want to measure precisely low momentum tracks. So one criterion there, for instance, was to have very lightweight detectors. And this is what I also showed. I mean, ALICE is trying to have these very thin, very lightweight detectors such that low momentum particles can be measured well. And so every measurement aspect, of course, has a dedicated optimization. So then the question is, do you want to be a general purpose detector, measure everything, or do you make more specialized measurements? There are other non-collider experiments. They are much more specific. They really choose all the detectors for very specific processes. So it really depends on what you want to measure. The principles stay the ones I showed, and this means that we know quite well how we have to build our detector to get a certain performance.
And of course, does these physics and engineering issues, has an impact on the study of new material? And so there's a connection between physics, engineering, and material science?
So yeah, I mean, there is a lot of technology development in this environment. I mean, one example, for instance, from the LHC accelerator technologies is vacuum technology, for instance, to get this ultra high vacuum in the LHC that allows to circulate particles for hours. You need very high vacuum quality. And there were, for instance, developments for surface coating, so-called non-evaporative getter, to really absorb all the molecules in there and provide this ultra high vacuum. So this was a typical material science development around the accelerator. In our detectors, there's of course a lot of development about these carbon fiber structures. We want the detectors to be very light. So the support structures, okay, they have to be rigid because we want to measure precisely, but they have to be light. So there's a lot of development on these carbon structures, carbon foam, and so on. So yeah, there's a lot of these, if you want, crossings between engineering and physics application in this environment.
Okay, so thank you once again, Dr. Riegler, for this very interesting talk. And let me thank you also our viewers and Deborah Bifaretti in the back office's directions. And have a nice evening. Bye-bye.
Thank you. Bye-bye.